A solar panel in the right orbit could collect up to 8 times more energy per year than a similar panel on the ground at Earth's mid-latitudes, such as in the US, Germany, China, or even Australia. But the words right orbit hide the key to that advantage. AI computers need steady electricity. Put them near Earth's dawn-dusk line, roughly along north to south poles, and they spend less time in the shadows. That lowers reliance on stored energy and heavy batteries. But it also pulls different power-hungry constellations towards related orbital paths. The shortcut to abundant solar energy may become a growing coordination problem. Space looks empty, so why would one orbit be the prime real estate? That answer depends on one number: eclipse minutes per orbit. Follow that number from batteries, proposed company filings, and cooling, to traffic and the view from Earth below. And we can begin to understand whether this is a bottleneck or simply a clever design choice. A sun-synchronous orbit is arranged so its plane rotates through the year and a spacecraft crosses places at roughly the same local solar time. A dawn-dusk version stays near the moving border between day and night, also known as the Terminator. An interesting name for an AI satellite. But because it's in the sun, it keeps the spacecraft illuminated through most of each revolution. Eclipse minutes per orbit tells you how long it loses direct sun and must draw from its batteries. Fewer minutes can mean less storage mass. But satellites still need reserves for failures, safe modes, and peak demand surges. However, this is still not one singular orbital ring. Altitude, inclination, local time, spacing, and phasing create a neighborhood of possible paths. Eclipse time makes that neighborhood valuable, but no one really owns it like a plot of land. Google provides the clearest technical case. Its paper models an 81 satellite cluster, and the company plans a 2-satellite learning mission with Planet for early 2027. That is a model and a small-scale test, not the same as a deployed fleet. But is Google alone in choosing this kind of geometry? An FCC public notice describes SpaceX's application for satellite groups at several heights above Earth, including sun-synchronous orbits, with lasers linking the satellites together. But an application is not an authorization. Data Center Dynamics reports that Cowboy Space has proposed 20,000 satellites in dawn-dusk orbit bands between 700 to 1,000 kilometers above Earth. Again, that is a proposal and not a committed deployment. The scale remains uncertain, but the pattern is worth watching. Power-hungry compute systems may be drawn towards related sunlit paths. If evidence-first space analysis interests you, then subscribe to Galaxial Frontiers, like this video, and leave a comment below on which orbital paths reign supreme above all others. Now back to it. Let's ask the important question of whether these battery savings still matter once we consider everything else the spacecraft needs. Saving battery weight is useful, but let's follow that savings through the rest of the spacecraft's design. In this orbit, a solar panel can collect more energy over a year than a similar panel on Earth. For a fixed energy target, that can mean less solar panel area, but it does not mean the arrays or batteries can become directly 8 times smaller. The satellite still needs power for continuous computing, inefficiencies, aging hardware, emergencies, and even spikes in demand. And space itself carries other costs. Vacuum has no air to carry heat away, so computers need radiators to shed heat. The satellite also needs radiation protection, maneuvering fuel, communications gear, spare systems, and a plan for replacement and disposal. Can't send a technician to diagnose a failed server rack, cooling pump, or spacecraft thruster. The US Government Accountability Office treats these as connected research gaps. So the real question is not simply, how much battery weight did we save? It is, did this orbit lower the total cost, or just move the cost somewhere else? It shifts part of the cost equation into shared operations. Put several orbital fleets into a related geometry, and conjunction screening grows. Operators need accurate positions, reliable contact, maneuvering plans, buffer zones, and safe disposal. Yes, networking satellites can be situated elsewhere and link back to Earth, but the power-heavy compute nodes still want low eclipse time. Cross-orbit links add changing distance, pointing, handovers, and coordination. That makes this resource a bit less like land and a bit more like radio spectrum. One user does not consume it all, but compatible use gets harder as users multiply. Additionally, dawn-dusk satellites can also stay sunlit while observatories below are in twilight, making them more visible to astronomers. The impact depends on their altitude, number, size, brightness, and design. The ring is a way to visualize this impact, just not a claim that it's impossible to overcome and coordinate around. The strongest countercase is that this never becomes an actual bottleneck. No orbital AI data center fleet has yet proven it can match terrestrial data centers on cost or reliability. Small prototypes may teach useful lessons without leading to giant constellations. Launch cost, radiators, radiation, maintenance, or communications could erase the power advantage. Operators could also spread satellites across different altitudes and local times, keep networking relays distributed, and reduce outside impacts with darker surface, better orientations, fleet limits, and stronger traffic rules. That is why proposed satellite counts are not a forecast. The real test is a full scorecard. Eclipse time, total mass and power, useful workloads, reliability, communications, traffic and disposal, impacts to astronomy, licensing and insurance, or in other words, the total cost. So why do AI satellite constellations all want the same orbit? Because continuous compute makes every minute in Earth's shadow expensive. Dawn-dusk sun-synchronous geometry can reduce the battery burden and improve annual solar yield. That's a real engineering advantage. It becomes prime real estate only when the value survives everything else on the scorecard and the design. If fleets scale, the engineering result suggests convergence. Power-hungry spacecraft choosing related paths and adding cooling, radiation, communications, maneuvering, and disposal work. The business result is that battery savings can appear as launch, replacement, coordination, insurance, licensing, and mitigation costs. Strategically, access to these orbital paths could become an AI infrastructure policy question before orbital computing is even proven long-term. Let's return to Google's solar energy comparison. Up to 8 times more annual energy sounds abundant, but that advantage exists because some orbital paths just get more sunlight than others. Space has no land deeds, yet its best solar addresses are not infinitely easy to share. The key question is whether real prototypes can turn that solar advantage into an economic one. Thanks for joining Galaxial Frontiers in this journey, and I'll see you in the next video.